state space analysis. So first of all, you should know and understand what is meant by state space analysis and why are we using this kind of state space analysis in the control systems. As you may be aware, that in our control systems we have mostly used this thing, transfer function model, right? State space analysis we are going to discuss. In the transfer function model, if you see, it is representing the complete system information. If you want to know particular state of the information, this state space analysis will be very useful. So in entire our electrical engineering or electronics engineering, the most important parameters that we are going through starting from generation to distribution is the three elements. One is resistor. You already know that. In the resistor, the power will get dissipated in the resistor. The power will not be stored, the power only will be dissipated in the resistance. So that the power that will be dissipated in the resistance we are calling as I square R. Okay, the power that is dissipated in the resistance is I square into R. Similarly, the other important parameter is inductor. Okay, this is most important parameter. The inductor will store the energy. Okay, so the amount of energy that stored by inductor is represented as half L into I square. The other important parameter is the capacitor. So capacitor is another energy storage element. The amount of energy that's stored in the capacitor is half CV square. So important to note that the inductor and the capacitor, these two elements is considered to be energy storage elements having memory. So memory in the sense something like this. See, in inductor you are not suddenly changing the current. Similarly, in a capacitor you are not suddenly changing the voltage. So that is what I mean. It is having a memory that it opposes sudden changes. Inductor opposes sudden changes in the current, and capacitor opposes sudden changes in the voltage. So this one we call as a causality. Causal functions. You may be knowing in your signal processing. You may be learnt about this causal systems. So in an inductor, the causal is the causal system, means the output of the system depends upon the input. So since the resistor is doesn't have a memory, we are not much bothered about the resistor. Only we are bothering about the inductor and the capacitor. Okay, this is the inductor. The current that is passing through inductor L, I am calling as the IL, and the voltage that is developed across the inductor I am calling as a VL. So the amount of voltage that is developed across the inductor, VL represented as L into dIL by dt. So here observe carefully. Here the current IL is a integral causality. IL is equal to VL by L integral. So the VL will go inside. Okay, 1 by L integral VL into dt. So this function is called the integral causality. Integral causality. So this causal function, that means the voltage is the current is the cause, voltage is the effect here. Okay, that is called causing. What it is causing? So the voltage is getting affected by whenever you are giving some amount of current to the inductor, the effect is resultant in the form of a integration. That is reason we are calling as a integral causality. What is the cause? That is what our aim is. So whenever the current is flowing, then the voltage is developing. So current is the source, voltage is the effect, source effect relation, or current is the cause, voltage is the resultant of that. So that is called integral causality. In the similar way, if you talk about the capacitor, okay, suppose the current through the capacitor you can say as C, the capacitor C, the current passing through the capacitor is IC, the voltage developed across the capacitor is say VC. Now VC is equal to 1 by C integral I dt. Here it is the same thing. Okay, due to the effect of current, the voltage is being developed. Okay, so this is again it is called integral causality. So if you wanted to see further, IC is equal to C dVc by dt also we can write that. Whereas in case of resistance if you take as a parameter, this resistance, this is a SI or SI unit representation of resistance. Somebody may represent the resistance as something like this, somebody may represent as box. So you have to we will use interchangeably with whichever we feel comfortable. So the current passing through the resistance R is IR, the voltage drop is VR. So this resistance doesn't have memory. So the voltage across resistance VR is equal to IR into R, or the current that is passing through the resistance IR is equal to VR by R. So now if you see the integration means summation means it is having some sort of a previous memory. So both the inductor and capacitor has the integral causality, whereas for resistor there is no preferred causality. Now how are we going to use this inductor, capacitor and resistor in our state space representation? Okay, generally the state space representation is represented as x dot, that means x differentiation dx by dt. X dot means a differentiation of x. X dot is equal to ax plus bu, y is equal to cx plus du. So what is a, b, c, d, what is x and what is y? I will just tell you one by one carefully. Suppose this x I am taking a small x, okay, small x dot. I am putting in the form of a matrix form. X dot and y is equal to, so I am taking as a, b, c, d, and here x and u. You observe carefully. X dot is equal to rho into rho ax plus b into u, bu. Y is equal to cx plus du. So it is simple. So we wanted to, why we wanted to take into matrix form is, as we have already studied, matrix is the one of the easiest way to see how the system response is going to change. And even most of the software that are available nowadays are also can be used to see these matrices. Okay, so now this A is called the state matrix. So this is A, one by one I'll write. A is called the state matrix. So what is meant by state matrix means this A is composed with all system parameters. I can say it is a system matrix also, or I can say the characteristics matrix also. So the entire system is depend upon the A matrix. Okay, so that is called A is the state matrix or system matrix or characteristics matrix. And B is represented as input matrix. B is input matrix. And C is output matrix. C is all the output parameters lies in the C, and D is the feed forward matrix. So now let us represent, how are we going to represent this, and what is this? Okay, so in this one the important thing is the x dot is equal to ax plus bu. This equation is called the state equation. This equation is called the state equation. y is equal to cx plus du. This equation is called the output equation. So you have to be understand very carefully. So we are taking only two equations. X dot is equal to ax plus bu, y equal to cx plus du. This first equation is called the state equation. Second equation is called the output equation. Okay, state equation and output equation. In the state equation, A and B matrices will be there. In the output equation, C and D matrices is there. Now we wanted to bring the causality into consideration, and we wanted to make some sort of a block diagram for this matrix. Okay, we want to make some block diagram. So block diagram representation of a state matrix. So now let me take one integral. Okay, let me take one integral. This is my integral. So for this integral, what actual integral will do? For suppose what I am doing is, I am giving a information of x dot. When I am integrating the x dot, obviously the output of integration is x. The differentiation will go. Integral of x is equal to x. So x dot is going to the integration. The output is x. So what are our equations? State equations. State equations is x dot is equal to ax plus bu, y is equal to, output equation is equal to cx plus du, right? So now x you got. So now this is a, now what do we want? X dot is equal to ax plus bu. So x is there. Now let us take a value of a. Okay, let us take the value of a. And x you multiply with this. So the output of this is what? Ax. Now you want to add to the x dot. So I will put a summation block here. This is summation. So this ax I wanted to add to, I am giving certain amount of input. U is the input. This u I am giving it to a matrix B. So this output is bu, right? So now you observe x dot is equal to ax plus bu. X dot equal to ax plus bu. Now y is equal to cx. So now if I multiply this x with c, the output of this is cx. And I wanted to add a summation block here again. This summation block I wanted to add u. See, very importantly, this u I am directly taking and multiplying with a d. So then it will become du. This du I am directly adding here. And I am representing this as y. Now we observe. If I keep everything in a box, something like this. If I keep everything in a box, something like this. Okay. So you are giving certain amount of input and you are getting certain amount of output. For a given input, there is a output. Okay. For a given input, there is a output. This is called the state space representation. Now, important thing that you need to understand is about D. See, this D information is not depend upon any of the system parameters. It is not depend upon integration summation. It is completely bypassed. Okay, this is called the bypass information. So directly bypass information directly you take from u and put it to the summation, or this is what we are calling as a feed forward matrix. So we are directly taking the input and adding to the output. We are directly taking the input, adding to the output. So why I mean, like where can generally in most of the state space equations you may not see about this information, du information, because du will add automatically some input to the output. For example, you are talking about DC-DC converter. If you are always adding some input to output, the output will be always higher and higher and higher, right? So that's why we generally not this thing. We generally go this way. So x dot is equal to ax plus bu, y equal to cx plus du, where D is the feed forward information. If you want, you can use, otherwise there is no issue to use. Okay, so some systems may have feed forward path, some systems may not have feed forward path. That depends upon what type of system that we are using. Now let us take some example and then we will develop the state space model. So let us take some example. In this example, we will try to develop some state space model of some simple RC circuit. So there is a resistance. So if you try to understand this one, everything will be easy. And there is a capacitance. So there are certain standard rules are there that you have to follow. Okay. So this is your input, this is your output. So this input I am calling as Vg. The output I am calling as V0. The resistance I am calling as R and the capacitor I am calling as C. Okay. Now, first of all, the first and primemost step, that is step number 1. Identify the energy storage elements. Energy storage elements. Now, tell me, in this, what is the energy storage element? That is the capacitor. Capacitor is the energy storage element. So, just recollect our main equation. Our main equation is saying like this: x dot and y, x dot is equal to ax plus bu, y equal to cx plus du, and when we try to write in terms of a matrix form, x and y, x dot and y is equal to matrix of a, b, c, d and x and u. So where x is a state variable, u is a input. Okay, now that state variable, how are we identified in the capacitor? Whenever the integration function exists, we identify that as state variable. U is the input, whatever the input that we are giving, that we called as a input, input. So here input is what? Here in this equation, the input according to our equation, U refers to Vg. U refers to Vg. Okay, and accordingly y is there. Y, so y is output. Output is V0. Y is V0. Now, the elements, what are there in the elements? Element is R and C. So, importantly, as per our first step, we have to identify the energy storage elements. So, this energy storage element here, it is only the capacitor is the energy storage element. So, in capacitor, what we have written, the integral causality, the voltage across the capacitor is equal to 1 by C integral IC into dt, where IC is the current that is flowing through the capacitor. So now, from our identifying the parameters, so x is a variable, state variable. So that means here we have to get what is the state variable we should get? Vc. Okay. Okay. Because the voltage across capacitor only we are considering. State variable here is Vc. Okay, Vc. Now, y is the output, is the V0. So now we have Vc or V0, both are same, because the voltage that is developed across is Vc or V0, both are same, right? The voltage developed across capacitor is equal to the voltage developed across the load also. Vc is equal to V0. Now, you have to observe carefully. Vc we know, C is a variable parameter. What is this IC? This IC we don't know. Okay. So, first of all, you have to bring that IC into action. What is IC? IC is the current that is flowing through. So, here the current here and current here, the load. Say for example, there is some sort of a load here. Okay. Current is there. The current that is flowing here. The current here it is flowing, say for example IR. The current it is flowing IL. We don't want to take IR and IL. Okay. Whatever the parameters are there, these 4 parameters only we have to play. That is input parameter, output parameter, state parameters. That's it. Okay. So input parameter is Vg, output parameter is V0, and state parameter is that C and R. Okay. So IC here, if you take node, so this is Vg, right? This is Vg input, this is V0 output. So the IC here, IC is equal to this current minus this current. As per KCL, what is happening? Incoming currents is equal to outgoing currents. So what are the incoming current? The current that is coming here, IR, is equal to IC and IL. So IC is equal to IR minus IL. IR is equal to Vg minus Vc by R. That simple it is. IR is equal to Vg minus Vc divided by R. That is IR minus IL. IL is equal to, say for example here the voltage, already voltage is V0, and V0 by, so the V0 by the resistance is the IL, right? V0 by the load resistance, I can say R0, V0 by R0. So this R0 is also called as one of the parameter because we are considering it now, because this R0 is just a non-dissipative parameter. If there is an inductor, then things are different. Okay. So now we want in the form of x dot, right? Now Vc we will integrate. dVc by dt is equal to 1 by C multiplication of Vg minus Vc by R minus V0 by R0. One important thing that you need to take into consideration, V0 is equal to Vc, right? The voltage drop across the output is equal to this voltage drop here. Okay. I will represent this V0 as Vc directly. V0 as Vc. Now let us segregate the terms. So first of all, the first parameter is identify the energy storage element. Once you identify the energy storage element, step 2, identify the parameters. Step 3, find out the energy storage element equations and convert that into the known form and then segregate. So here the segregation will happen. So dVc by dt is equal to, first of all, this Vg minus Vc by R into C minus Vc by R0 into C. Okay. Now you take the input output separate. So Vg is the input, Vc is the output. Okay. So now Vc I am taking as parameter 1 by Rc here. Okay. 1 by Rc minus 1 by R0 into C. Okay. Minus this is minus. So this is Vg, right? This will become plus Vg you take common, 1 by Rc. See, here the plus and minus plays a very important role. Okay. Why? You observe carefully. Vg minus Vc by R minus V0 by R0. So I have taken current. Current here is Vg minus Vc by R. So here I have taken only this V0 by R. So this IL is equal, this is IR incoming current is equal to IC plus IL. What I want is IC. IC is equal to IR minus IL. IR is, see, sometimes you may take V0 minus Vg by R also you can take. And you can take V0 by this also you can take. So there is no harm whether you take from Vg minus V0 by R or Vc minus V0 by R. But it depends upon the how the current is flowing. Now the current is flowing in this direction. So if I am taking, this is high potential, this is low potential. and current is this position. So this is high potential, this is low potential. Okay, like this. Depending upon the potential difference, this minus will be decided. Okay. Now, this is in the form of x dot is equal to ax plus bu form is there. So where a is the state information. So you can observe carefully, all the elements R, C, R naught, whatever the elements are there, all the elements are there in the A matrix. That is the reason why it is called the state matrix. Okay, B is the input matrix. So the input is depends upon these two elements R and C. So that's why I'm writing input here. Now output matrix. Observe carefully. There is no feed forward. There is no direct path between input and output. So D is equal to 0 obviously. Now Y is equal to Cx. X is here Vc. And D is 0 and U, right? So here observe carefully. The output Y is the output in terms of Vc. So V naught is equal to 1 times of Vc. That's it, because V naught is equal to Vc and 0 into U. Now you got A, B, C, D parameters of this circuit. Guys, any questions you have? Okay, so you try to understand it carefully. So what I did is very, very simple. I'll just do it. So first of all, if any circuit is given to you, just that circuit you wanted to find out the state space analysis of the circuit. So the important thing that you need to do here is, first of all, find out how many number of energy storage elements are there. Okay, so the number of energy storage elements is the 1. So the system is a first order system. Okay, you already know this. Now what our aim is, find out the number of state elements what are there in this. So there is an element called R, there is an element called C, there is an element called R naught. So R, C, R naught we have taken. Now find out what is the input and output. Input is Vg, output is V naught. So Vg and V naught. Now it's clear. After that, what are we doing is, our main interest is on the energy storage element. We have already known that energy storage element, the voltage across capacitor is equal to 1 by C integral IC into dt. So directly we are taking 1 by C integral. So here IC is not all there in our list, right? So this IC is not there in our list, and hence what we want to do is, we wanted to convert this unknown parameter from a known parameter. This is how we are doing. So IC, that means the current that is entering into the capacitor is the current that is flowing here minus the current that is flowing here. So that is Vg minus Vc by R minus V naught by R indicates the IC. That is what I have doing. Now we want in the form of a differentiation, right? X dot. So dVc by dt, I am differentiating on both sides. This integration will be out. When integration will be out, and I am segregating this input and output way, I am segregating this. That's it. So that's how this I am making a B, C, D matrices. Now let us go for one more example so that you understand further more clearly. So now see, why I am telling this A, B, C, D parameters, you can know each and every state information of a system. That is how you will know the A, B, C, D parameters. Okay. Now let us take another example. This is say example number 2. So tomorrow you have to be solve all these things in our tutorial class. For now you take the example 2. So let me take a RLC circuit. There is a R, there is a L, there is a C circuit. So the input that we are giving is here Vg again. That means input voltage, and the out, and assume that there is one more load called R naught. Okay, so this one I am calling as a R1. This one let me take as a R2. This one I am taking, let me take as a L. This one I am taking as a capacitor C. And the current that is flowing through the L I am considering as IL. And the current that is flowing through output I am considering as I naught. The current that is flowing through capacitor is IC. Okay. So first of all, you have to remember only the two things. Okay. So what are those two things? That is how many number of energy storage elements. So here there are two number of energy storage elements. One is inductor, other one is capacitor. There are two energy storage elements. Now you just recollect what is the equation for inductor and capacitor, what we have written. In inductor, what we have written? IL is equal to 1 by L integral VL dt. So you know already. So what is the causal? Integral causality. Okay. For the capacitor, what we have written? VC is equal to 1 by C integral IC into dt. These are the two things that we know. Okay. Now, these are the two things that only we know. Okay. So, and we told L is one parameter, C is other parameter, R1 is other parameters, R2 is also another parameter that are there in the circuit. And we identified the inductor current, voltage across the capacitor. Okay. So now, this here you try to understand carefully. This is second order system. Okay, second order, because two energy storage elements are there. Now, our state space analysis indicates x dot is equal to ax plus bu, y is equal to cx plus du. So, since there is no direct connection between the input output, so there is no feed forward, so d is 0, only c is there. Now, what are the x parameter here? That is state variables. Okay, so since there are two energy storage elements are there, so one state variable is IL, another state variable is VC. Okay, IL and VC. These are the two state variables. Now we have to put our equation in this form. First of all, let us take that IL. Okay, so IL is equal to 1 by L integral VL into dt. Okay, now 1 by L. What is the voltage drop across this? So if you make a Kirchhoff's voltage law, this input voltage is equal to voltage drop across resistance plus voltage drop across this inductance plus voltage drop across this capacitance, right? So now Vg is equal to, say, voltage drop across resistance, since already current is IL, is into R1, IL into R1. The voltage drop across inductance is VL. The voltage drop across capacitance is VC, right? Now 1 by L integral. So total voltage Vg is equal to here, Vg is equal to IL into R1 plus VL plus Vc. So now I want only VL. VL is equal to integral Vg minus ILR1 minus Vc. It's very simple. We brought the unknown VL into known variables of Vg, IL and Vc. So, but in the state space, what we want is a derivative. So, let us derive this. dIL by dt is equal to 1 by L. So, integration will go out. So, integration is here Vg minus IL R1 minus Vc. Now, segregate this. Okay, now let us segregate this. Input and output way, you will let us segregate this. Now, dIL by dt is equal to input and output. So, input let us take out that side, output you will take this side. Okay. So, minus R1 into IL, minus R1 into IL divided by L minus Vc by L plus Vg by L. Okay, so this is very simple. Though, so these parameters is in the IL and VC form. Okay, IL and VC form, and is having a VG also input. So now let us first of all make some equation. IL dot and VC dot. These are the X dot, right? X dot is equal to, so this is A matrix and X. So X are the state variables IL and VC. Now you observe carefully. You will relate here. So IL is minus R1 by L, and VC is minus 1 by L into VC, plus X dot equal to AX plus BU. BU. U is the input. Input is VG here. So for the numerator it is 1 by L. Okay. Now what is the second? So we need to find out the VC dot, right? That is the first phase. Second is VC dot. Now what do we know from the VC? So first of all you have to find out here. So VC is equal to 1 by C integral IC into dt, that we know. VC is equal to 1 by C integral IC into dt. So now what our aim is, we need to find out current that is flowing through the capacitor. Okay, so the current that is flowing through the capacitor is, so this current minus this current is the current flowing through the capacitor, right? I'll simply write down that. So 1 by C integral IL minus I naught. So C is a parameter, IL is a parameter, but I naught we don't know. What is I naught in terms of, I want the state parameters. Okay, I naught is equal to 1 by C integral IL minus I naught is equal to V naught by R2. I naught is equal to V naught by R2. Now simple, that's sufficient. Now it is in the form of input and output. Okay, output is V naught, right? So V naught output. So this is in terms of V naught in terms of, so V naught is equal to IL VC. V naught is equal to Cx plus du, that d is always 0. Now you observe carefully. Now I have to differentiate this Vc dot I want. dVc by dt is equal to IL by C minus V naught by R2 into C. So there is no Vc term here. Okay. Now you can simply see that, you can simply see here that Vc dot is equal to IL by C. Okay, IL by C minus V naught equal to Vc minus 1 by R2 into C. That is sufficient. And there is no term associated with Vc. So this is done. Now the output is equal to V naught equal to Vc only. IL, there is no IL term, 0, 1. This term is 0. This simply, so this you take as A, this you take as B, this you take as D. Okay, this much simple it is. So once again I will tell you, just for our recap, understand it carefully. First thing is, you take a simple RLC circuit. This RLC circuit is, I am taking having resistance R1, inductance L and capacitance C, and there is a load of R2, and here the voltage drop is V0. This V0 is equal to Vc because those two are in parallel. First of all, we have to find out that how many number of energy storage elements are there. So there are 2 energy storage elements. So then the equation will be two second order equation having 2 terms. Okay. So first of all, we have to find out the equation for inductor and capacitor. IL is equal to 1 by L integral VL dt, Vc is equal to 1 by C integral IC into dt. What are other parameters that they have given? Input as Vg, R1, L, C and R2. These are the parameters. So whatever the equation we want to represent, this has to be in the form of this. Now what we know from the state space, x dot equal to ax plus bu, y equal to cx plus du. There is no direct relation from input to output, so d is equal to 0, y is equal to cx. Now x is a state variable, so since there are 2 energy storage element, 2 state variables will be there. What are the state variables? IL and VC. So IL and VC will be your state variables. Now once you get the state variables, you find out the ABCD matrices. So in order to find out ABCD matrices, take the inductor equation. IL is equal to 1 by L integral VL dt. IL is equal to 1 by L VL. The voltage drop across inductor is equal to input voltage minus voltage drop across resistance minus capacitor voltage. So 1 by L Vg minus IL R1 into Vc. So everything is in the form of known parameters. So we will segregate the input and output. So there is one parameter of IL, there is one parameter of Vc, there is one parameter of Vg. So IL, Vc and Vg parameters are taken. Now there is second thing, second capacitor equation. Vc is equal to 1 by C integral I dt. Ic is equal to IL minus I naught. So where is I naught is a not known parameter to us, let us bring into unknown value, unknown to known value, V naught by R2. Vc is equal to 1 by C integral IL minus V naught by R2. So, and we need to differentiate. dVc by dt is equal to IL by C minus V naught by R2 into C. So put that value IL and C here. So there is no term related to the input. So I am making it to 0. Now let us bring it to output. Output is V naught. V naught is directly linked to Vc. There is no IL term is indicated here. So V naught is equal to directly Vc. So IL term will become equal to 0. D is always 0. So this matrix is A matrix, this matrix is B matrix, this matrix is C matrix, D matrix is 0. This is the simplest way of representation of your state space analysis. You can extend this state space analysis to any sort of DC-DC converter, DC-AC inverter, and then most importantly to our control systems.